We're almost ready. Huh? Okay, we're ready. So it's my pleasure to introduce Kathleen Gates. She is assistant professor of psychology at the University of North Carolina, Chapel Hill. Did I get that right? And she graduated from high school, I don't know which. She attended and graduated from Michigan State, took a master's degree from the City University of New York, and a PhD at Penn State. And I came across some of her work a few years ago and was astonished that it was so brilliant and so ingenious and so able to be done without my help. And I'm just delighted that she's here, and please welcome her.
And now University of Pittsburgh. So thank you for having me for this talk. So I'm going to be talking about clustering heterogeneous samples during model selection. And first I have to acknowledge the co-authors on this project, a few of them who really did the programming and made this all possible. This is my student team, and so I'm working very hard on this, and this can be possible without their help. So when I'm talking about heterogeneous samples, what exactly do I mean by that? And so, so we're all on the same page. I'm talking about samples within which you have individuals, and they vary in their temporal processes. So in the case of fMRI, that would be individuals with different brain processes, as evidenced by their functional connectivity patterns. And so another main point that I'm going to be returning to is that this occurs often in fMRI, and that this is a problem. This is a problem for modeling, and this is a problem for arriving at inferences that are reliable and valid across groups. And then the final point is I'm going to introduce one solution, of which there are probably many, that might help to arrive at these reliable group, subgroup, and individual level paths. Because if we do have heterogeneity, and we have individual level paths for everybody, it can be very difficult to make sense of it. And so that's why coming to subgroups and finding similarities across the individuals could, I think, really help. And then also, of course, group level paths, and we can have our nomothetic, what is constant across individuals. So just an example of how much people can differ. This is just one individual. It's pretty typical in terms of the number of additional paths that they have in the sample. This was a paper headed by Adrian Belt at Penn State. And we have here the group level paths, and these are thick lines, and so anything that's this thick, that means that everybody in the group had it. Same with this autoregressive path, which is how this region at time predicted itself at the next time point. And so we see here a number of additional paths for that individual. And this is why we argued that using just the group level path, we're really missing a lot of nuances that would be important to understand the individual brain processes. And so here we used, we broke individuals up into 4 groups based on their performance and looked at the subgroup level maps that arose. So we broke them into the 4 quartiles first, and then ran analysis to come up with a subgroup level map. The subgroup level maps here all matched on to what we did when we had all of the individuals together and came up with the group level maps. So we graded them out because everybody had the same path. But then we saw that with, this is the upper quartile, the best quartile, people who performed the best on a working memory test, they had fewer paths in addition to the ones that were found in the group, whereas they got worse and worse, they had more paths. And I didn't depict here the individual level paths, but when we did, quartile 1 had the more individual level paths, so they varied more from kind of this canonical group level path. And then we can further look at subgroups. We looked at subgroups again for successful learners and non-learners. But these were all, and it kind of was the same idea that we're going to try to figure out who is not learning and what is the brain patterns depicting that. And then what is the markers of successful learning for learning a new language, and this is Cantonese. But the problem is that we arbitrarily place those people into subgroups. We place them into subgroups based on performance, much like we, as science, place people into subgroups based on gender, or we place them into subgroups based on age, or diagnostic category. And these are all arbitrary dimensions, because you can place people on subgroups based on anything. You could come up with anything to place people into subgroups on, but we don't know if that is the best subgroup for them. Is that the subgroup, or are they actually being placed with people that have shared biological underpinnings, or are they being placed with people just that have shared behavioral variables, or for instance, demographic variables. And so when we are placing people into groups a priori, we're doing it rather arbitrarily because there's so many dimensions upon which I can classify any one individual. And so it's a little bit backwards to then look and say, how are these groups different? It could be. And so this is, I'm just suggesting a complementary approach to kind of how we are currently doing things in science. And then added to that, there's often heterogeneity within groups. So even if I do separate people by male, female, or ADHD diagnosis, non-ADHD diagnosis, then within those groups, of course, there's going to be heterogeneity. All you have to do is talk to two people who are within the same group, and you'll see that they're going to be a little bit different. This is very prominent in ADHD and ASD, autism spectrum disorder literatures, because you see such heterogeneity in the symptoms as well. So it's also manifested on in the brain level. And so defining people based on ADHD, non-ADHD is kind of setting, I think, researchers up to not be able to replicate their findings, because typically developing controls are going to be heterogeneous, and ADHD are also going to be heterogeneous, which I'll also show a little bit later. So this is kind of suggesting a call that there might be some use for data-driven subgroups of individuals based on their brain processes. This is what I mean in pictures. So here we have two different types of brain processes. These have the red lines going under, and these have green lines going above. And how we typically do research is we will categorize them based on some arbitrary dimension, female, male, or ADHD, typically developed in controls. So what I'm proposing is to organize people based on their brain processes. And then we might be able to see, once we organize on this, we might have similar findings. We might say, okay, they do actually cluster according to diagnostic category, and that is an appropriate way to cluster given these brain regions that we're using. Or we might find that there's two subgroups within a given population or a given sample, and that and this is something that we wouldn't be able to find if we had just separated them based on ASD and control, for instance. So we're not the only ones in my team doing this. In the past year, we have seen 5 other people publish exactly on this heterogeneity problem. And so we're kind of hoping that this is good timing for it. And the ways that this could, I think, help with some sciences, or in the science, is that if we subgroup people according to brain processes, we can check that the predefined groups are actually the best dimension upon which to categorize people. So, for instance, maybe ASD versus typically developed controls isn't the best way to organize people given the brain regions that we're using and the task that they were doing. Maybe actually it's differentiated better based on age, if for instance it's a visual task. And then researchers can also identify biological underpinnings related to specific behaviors in heterogeneous samples. So if I have, for instance, my sample of ADHD, I could see which biological underpinnings relate to what symptom set of behaviors. Now, before we go into subgrouping, we need to figure out how to come up with reliable individual level models upon which we can take those features and then subgroup. So we're going to take a little bit of a detour away from subgrouping and heterogeneity to talk about how we can come up with individual level models that are reliable. And what I'm going to be talking about is all embedded within unified SEM, unified structural equation modeling. And this is just a little example here. We have 3 regions, and a solid line indicates that it's a contemporaneous relationship. So that means that when that changes in the right prefrontal cortex are related to changes in the left prefrontal cortex at time. So at the same time, as one goes up, the other one goes up. This lag effect denoted with the dash line, and I'm sorry for the formatting. We switched from Mac to Windows, and apparently not everything's perfect. But so this indicates that, in this example, that activity in the amygdala at t-1 is going to predict activity in the left prefrontal cortex at the next time point. And here, for those who feel more secure with the quick equations and want to see it formally, we have A being the contemporaneous matrix, phi being the lag matrix of effects, and eta being our observed variables, and then we have theta, our errors. And so, yes?
Just, so when you have contemporaneous, but you have an arc, what is the arc indicating there? Is it causation, like hypothesis of causation, or?
That is, I think, to be determined. So when we simulated this, and I'll show the results a little bit later on the Smith data, which did have a causal model where they started with the neuronal level activity and then ran a blue model to come up with the gold, and we were able to recover that. I am always a little bit hesitant to ever say we can ascertain causality with a contemporaneous relation, but given the time lag of the gold data, I think it's the best we can do.
Okay.
Because the lag, of course, is that 2-second or 3-second lag, and that's milliseconds. Yeah. So I feel more comfortable saying at this point statistically positive.
So the choice of the eta t on the left-hand side, it's not t plus 1, it's t, is it?
Mm-hmm.
How do I understand that? Because
so right here for the phi, or I don't know if it's easier.
No, on the left-hand side of the equation is eta t.
Right, so we have eta t equals eta t. On the A matrix, the diagonal is zeros. So it's just a handy way to depict this, that they are the same variables, but since the variables in eta, so like can predict other variables in eta, but then you just zero out the diagonal so they can't predict themselves. So like amygdala can't predict itself at time.
And is there any specific form for the error vector?
For, it's usually considered to have uncorrelated errors, but we can easily add them in. Yeah. Okay, so just to drive home another reason of why not to do group level analyses is that when we conducted group level analyses where we concatenated individuals, we arrived at a pattern that described no individual. And so here's a little toy example depicting that. We have these two participants, participants 1 and 2, who are identical. Participant 3 is identical except for this one path is reversed. Instead of having 1 predict 4, as we see in participant 1 and 2, we have 4 predicting 1. So it's a quite minor change given all of the other similarities that they have. But we knew that this would perpetuate throughout the correlation matrix. And when we conducted the analysis on the group level, we first arrived at these two paths that were going bidirectional, they were contemporaneous, and they were negative, even though in the simulated data they were positive. And then a spurious path resulted between variables 2 and 4. This is just a spurious result waiting from the correlations induced by switching this and then concatenating. And so this is just a little toy example of how when you do have heterogeneity and then you arrive at group level mass, you could arrive at something that doesn't really describe any of the individuals comprising your group. And so just another point for making individual level data more common. But then we have problems with individual level data, as I know many people here are aware. When you do individual level data analysis, it can be driven by noise. You can arrive at a model that can be spurious or could miss connections. Smith et al. Did kind of a landmark paper in 2011 where they tested 38 connectivity methods on 28 sets of data. No method really did well at recovering both the presence and the directionality of data. Our method, USEM, was not tested, but when we tested it, it didn't do well. It recovered the paths, but it couldn't get directionality done, and we kind of followed the same pattern as our colleagues here. So, but there's no need to fret because we did some follow-up work, and we are, getting better and better at getting individual level paths. First off, here at CMU, of course, the Lingham-inspired approaches have done excellently well, and I was amazed last night to hear from Joe that he can now scale it up and do it at the voxel level. So I continue to be in awe. Clarksburg. And then we developed a little approach, group iterative multiple model estimation, which also was able to, is able to come up with both the presence and the directionality of effects. And so I'll show you here how we are doing that. We do it in a forward stepwise procedure. So we start with a model that has no paths, and then we open up paths that are going to improve the model statistically for the majority of the individuals. So in this way, it's not going to be influenced by outliers. So if one model, one individual is going to be improved really greatly by a path, but all others are very small, then when you average that together, it can still be quite large effect. But so we don't want to be driven by outliers, and so we just take how many people will this path, if opened up between two regions, will improve the model. And so we use modification indices to identify what path, excuse me, let me back up a little bit. We use modification indices to first identify how much each path would improve a model. So I take an individual and I look at the modification indices, which tells me how much I can expect the model to improve should I open up that path. And if it's significant, then I count it, and then I count how many people for whom that path would be significant, and it's significant improvement. And the paths, the modification indices are chi-square distributed, so it's asymptotically chi-square distributed, so it's fairly easy to detect whether or not it's going to be significant or not. This is my thinking behind it, and I think this kind of helps explain things a little bit more. If we were doing a meta-analysis, and I had one sample across n individuals, as we typically do in a cross-sectional study, and let's say that I was doing a meta-analysis, so I had 4 samples, and what I would probably do in a meta-analysis is I would look across these to see which effects were significant across all of those. You're trying to find consistency across samples. And so I'm viewing the functional MRI data in the same way, where now our sample is one individual. So instead of having 1 to n, we have 1 to t here, and then t being the number of time points. And so instead of the samples being the sample across maybe regions of the state or something like that, we have different samples across individuals. And within that, and we actually have many more samples than we have in a meta-analysis. So we can view this as if we had a system that we were trying to test. Like, let's say I was trying to test a brake system in the car. I would run it a lot of times, and I'm going to see for how many times does it work. So kind of along those same lines of thinking, if we can consider our samples from the viewpoint of we're trying to come up with something that is nomothetic or the same across all individuals, by testing each individual, we should come up with these effects that are common across them. And so that's kind of the rationale behind choosing the ones that are most significant for people rather than concatenating them and just choosing the effect that comes up, because I've demonstrated what happens when you concatenate and then come up with a model and you have heterogeneity. So this is what it looks like. We start with with an empty model, and then one by one we open up the paths. In functional MRI data, it tends to be the autoregressive paths that are opened up first because there's such a lagged influence. So we arrive at our group level map, and then we can also arrive at individual level maps. So like right down here, we have our gray paths, which would indicate person A, person B, and note that they all have the same group level paths. And so when we tried this on the Smith data, we got some pretty good results. This is taken from the paper that we wrote a few years ago. Since then, we have been able to identify the directionality 100% of the time in the Smith program. We moved over from a MATLAB literal version to our package, and we get better recovery. And we can also detect connections that exist on the individual level. Yes.
Is this using all of their 50 simulated subjects at once?
Yes. We've tried it in batches of 10, and it works very well. It works. There's no difference from here. But we do need at least 10. If we do use even as low as 5, it doesn't work as well.
So those individual level conditions, you model those, create those, because in simulations all the subjects have the same structure, right?
I'm sorry.
So those individual level patches there,
Mm-hmm.
when you make your simulation, you create them?
Yeah. So we simulated data and then we create these on top of the group level just to see, to make sure that we could recover them. So then we felt perhaps overly confident with our successes so far, and we made really messy data on purpose to kind of tax our system and see how well it can do. And let me just move this out of the way. So that'll go away. So we have here we simulated data for 4 subgroups. For each color, it denotes a different subgroup. Here we left out the gray paths, which would indicate the individual level, but just know that for each individual, they had 2 paths randomly opened. So they have 4 group level paths. In addition, everybody has autoregressive, just that's what we see in MRI. And then 5 group level paths, some lagged and some contemporaneous. We have subgroup level paths denoted by the different colors. The subgroup level paths, we opted for 4. In empirical data, we see anywhere from 2 to 7. We did a little bit of lip search to see when people do have subgroups, how many paths do they usually have in addition to the group level path. And we've just found 2 to 7, so we settled on 4 for this example. 4 extra paths per subgroup. And we did a few simulations. I'm showing here the 4-group simulation. We made this across 25, 100, and 200 number of individuals. Number of subgroups being 2, 3, and 4. So for the 2 subgroup condition, we just don't have these orange lines and the magenta lines. And for the 3, we don't have the magenta lines. So we have different number of subgroups. We have different number of individuals. We did 25 instead of 10 because we didn't, the end goal, right now we're just still trying to figure out how to get the individual level paths, but the end goal is to subgroup them. Subgrouping 10 individuals probably won't be very illuminating, I mean, it is a small sample, and so we didn't even test it for 10. We just tested it at 25. We figured that would be a lower minimum that people might try to do this on. Because, for instance, you might have 25 people in a classroom or something to that end. And then we also varied the degree of heterogeneity. So we had one subgroup. So for half of our simulations, we have equal subgroups. So for the 2 subgroup case, they're 50-50. For the 3 subgroup, there's 33, 33, 34%. And then for our 4 subgroup case, everybody has 25. Every group has 25%. Every large group is comprised by 4 equal parts, 25% of the subgroups. But then we wanted to see what would happen when we had more of one subgroup, and if that would mess up things in terms of having spurious group level paths or not being able to subgroup appropriately. So we added this part in to see when we kind of make things harder on our system to identify what is a subgroup versus a group level path, what's going to happen. So when we did that, just the regular gimme results without subgrouping, we recovered 92% of the paths, and we recovered 88% of the directionality, which isn't perfect and could be improved upon. But when we ran it through, and then we also created a data simulation. I'm sorry again about this formatting. But when we simulated data where the only thing they had in common was autoregressive paths and then having an external stimuli, such as you see in event-related design, and then everybody just randomly had paths open, we were able to recover 100% of the connections with 94% of the correct directionality. So you see that with that we're doing okay pretty well when we have a lot of heterogeneity. When we did the individual level approach without using the group level gimme approach, then we only recovered 83% of the path, and the directionality was no better than 50%. So tossing a coin. All right, so now we need to get back to subgrouping. And so just really quickly, this is the type of thing that we're looking for. Are these individuals, perhaps, can we identify basically, my driving purpose is to identify subgroups within heterogeneous samples like ASD or subgroups that we think we have already grouped. So if we think we have typically developing controls in ASD, but the ASD might actually have a lot of heterogeneity, and how do we make sense of all of that heterogeneity? So this is what it looks like in the format that I've been using without the brains, and so we're trying to identify how if there are systematic deviations from this group level map in the types of paths that are existing in individuals. our first pass at this, we did subgrouping after conducting BIMI, and what we did was we parcellated the brain to get the frontal parietal region. We arrived at individual level maps and group level maps. One group level map where everybody had, excuse me, their own path estimated, so everybody has varying weights for the group level paths. We then took the group level paths, since we knew that they would be normally distributed, the beta weights would be normally distributed across them. And when I mean beta weights, I just mean each path isn't 0, 1, each path has a weight saying how strong the connection is between two, and it could be positive or negative. So we took everybody's beta weights. They have a matrix. We vectorized them, and we correlated their the group level ones to come up with a correlation matrix. So this is not a correlation matrix of regions. This is a correlation matrix of people. So across here we have one group N and one group N of how people are similar to other people. Then we use community detection to cluster them. So now we have clusters of individuals that share some similarities in their group.
Sorry, how did you cluster?
We used the fast modularity. It's in the MATLAB toolbox for the scores toolbox. And what we did was we, and this is what we're currently improving on, is that we dichotomized this. Because at the time, even though this was published in 2014, at the time of analysis, there wasn't the quantity of weighted approaches for clustering individuals that we see now. There was a lot of binary approaches, or approaches that used expect 0, 1 matrices. And but since 2006, I think is when Newman came out with a paper. He came out with one in 2004 and one in 2006. And since 2006, it's just been an explosion of new community detection techniques. And so now we have a lot of weighted ones. But for this one, we dichotomized it based on a threshold. We went through a very arduous process to come up with the threshold. We tried out every single threshold. And then we came up with subgroups based on a dichotomized matrix of this. And so that's great then into modularity and then how we're going to choose our community detection approach moving forward. So modularity is used in a lot of community detection approaches. Community detection, for those who don't use it or aren't too familiar, is cluster analysis. You can think of it as cluster analysis. It's clustering people according to similarities. So you want more similarity within group than between group. And so it's often used in networks, and so instead of similarity, it's thought of in that case in terms of connection. But we're bringing it back to similarity. So kind of started in social sciences, we're bringing it back to social science interpretation, that we're considering our matrix of, that I showed you in the previous slide, this matrix, our similarity matrix of how similar two people are. And if you find a cluster of people who tend to be similar with each other, that person A is similar to person B, who's similar to person C, who's similar to person A, then that would be a cluster probably. So modularity was introduced by Newman in 2006 to find a cutoff, because most clustering algorithms either start with everybody in their own group or everybody in the same group. So in the case of, let's say, if it's an algorithmic approach, everybody would be in their own subgroup, and then you would merge people together who are the most similar, and you would keep merging groups together like this until eventually everybody's in the same group. So you could keep doing that. And the problem is, that has been kind of plaguing social scientists, is when to stop it. And so Newman came up with modularity, which is a stopping mechanism for when to stop clustering. And so in this example, we see Q, modularity, is at a peak at the second cluster, and so that's where the division would stop. So this is modularity in a nutshell. And there are a lot of approaches for it. So we used a modularity-based approach for this paper, and we found 5 subgroups. Here's the group level map that has all black on it. 5 subgroups, and here red denotes that this path is higher on average than the rest of the groups. Blue denoting lower on average. And we, this is to me the most interesting part, because I'm not a neuroscientist and don't really know how to interpret brains. But this to me was most interesting, is that we found that controls were more likely, statistically more likely, I missed the chi-square on here, but it's statistically significant. Controls were most likely to comprise subgroup A and subgroup B and ADHD individuals. And then you have subgroup E, for instance, which is kind of odd because they're split in between. And when we look back at this brain pattern, we see this brain pattern emerging a lot. These are all parietal regions emerging a lot in people who are undergoing trauma and stress. So I thought that was kind of interesting that perhaps this is kind of a mix where some people are manifesting behaviors of ADHD in response to a stressful situation. So this is, again, within ADHD, typically developing controls because you wanted to see if we would be able to parse them out. But also what I thought was interesting is that the controls have a lot of heterogeneity as well. And some of them have maps that are similar to the ADHD, yet they're below the threshold for the diagnoses. But still maybe higher on symptoms. It's just resting state. Mm-hmm. Oh, and I should mention, so this was gathered by Joel Nick and Damien Fair at Oregon Health and Science University. All right, so then we wanted to continue doing this, basically, but when we looked into approaches for weighted community detection algorithms and kind of started studying them and learning a lot about them, but we couldn't find one approach that kind of percolated to the top as being best for correlation matrices. Even though they're used in functional MRI research a lot on correlation matrices of regions of interest or voxels. So then you have voxel by voxel, and you run community detection algorithm on it, and you get your clusters of which regions cluster together. The problem is that most of these, with the exception of fast modularity, they were tested on weighted correlation matrices that were sparse and count matrices. So you would have maybe 0, 1, 2, 3, 4, and then they did examples. They used examples such as how many papers have you published with certain people, which is a count. And so these were all tested on count matrices, and correlation matrices have very different properties. There's interdependence among the elements, and they're dense. There's typically no zeros in a correlation matrix. Excuse me. And so we did a little Monte Carlo simulation to see which one was best for our purposes, because we want to be able to run the analysis on the correlation matrix, and Walktrap was far superior, even though InfoMap looks pretty good here. It's either doing really well, 100% recovery. I'm sorry, I should explain. The y-axis here is the adjusted RAND index. And so it indicates how well the subgroups that were recovered relates to the subgroups that were used to generate the data. And so you don't need to read all of this. I just want to draw your attention to the Walktrap that it did exceptionally well. Red are the correlation matrices. We did try Euclidean distance matrices, but none of them did especially well for that. And so we see this is for n equals 25 all the way up to n equals 1,000, because again, we're only concerned with, we're not using huge data here. So for our purposes, we're going to move forward using Walktrap for weighted correlation matrices. So we don't have to dichotomize. So this brings us closer to subgrouping within group iterative multiple model estimation. So first we're going to start exactly how we did, and one by one we're going to choose the group level map, just as we did with the regular giving. And so we're going to use our modification indices. And then we are going to conduct community detection on the similarity matrix. Now the similarity matrix here was a point of, it's a very important decision. So community detection is only going to work as well as the features that you use to select, right? So if I'm feeding core features into my community detection on which to separate groups, then it's not going to work. I need to have very good features. So feature selection was really important to us, and so we tried two. Well, we tried many, but there's two that are worth presenting, basically. One would be a similarity matrix that is the correlation matrix of, so much like we did before, we took the correlation matrix of regions that were simulated, vectorized them, and then took a correlation of those, Fisher transformed, and then took correlations of those. So then we get a new correlation matrix that is the similarity of people by people. Second approach we tried, and then I'll present here both, we used the modification indices. So remember, for group iterative multiple model estimation, we are selecting paths based on modification indices. After the paths are selected for the group level map, the only modification indices we have left are the ones for the next round, for the individual level. So we thought that using the modification indices would actually subgroup better, because we've already taken out everything that's related to everybody on the group. So when we have a correlation matrix of all individuals, and we vectorize and look at that correlation matrix, what's contained in there are all of the similarities that are going to be recovered in our group model. So by conducting community detection using the modification indices, we thought that we would better be able to tease out these subgroups. So we do it that way. Oh, this isn't going forward. Okay. So then having arrived at a subgroup level map, having arrived at subgroups, we then, within each subgroup, arrive at group level maps, but now they're subgroup level maps. So they all still have the group level paths, and now we add paths that exist only for those subgroups. And the rationale behind this is that following from the logic that the group level paths improve upon recovery of individual level paths, if we could then get subgroup level paths, we could further improve our reliability for the individual level paths, right? Because if you imagine that you have 200 individuals and then you subgroup them into 50, having any information on those 50 would help improve those maps for all of the 50 people in that subgroup, right? Because again, as shown before, when we did individual level maps, we didn't recover directionality any better than chance. We had to have some sort of group level prior. So having some subgroup level prior might further refine our search for the individual level. And we get subgroups, which we can then look at. So then after we get our subgroup level model, we then conduct our search for our individual level models just as before, again using the modification indices to identify which path would best improve that individual's model, adding those paths until the model is excellent via various fit indices. All right, so I mentioned two of the benefits is that one, we can better tease out signal from noise because the group level similarities are used. So we're only using modification indices after the group level. So we're really looking at having taken into account the group level paths, what paths are going to be similar in people and how can we question people according to that. And then our individual level paths being more reliable for the reasons I just stated. This, I'll just go through quickly. I'm not sure how interested people are going to be in this, but some people prefer to have it framed in terms of equations. So here we have our group level estimates. The I here indicates that each individual will get its own estimate. So again, these are all weighted estimates. And then we will arrive at our subgroup level matrix of effects. And so again, every individual will have a subgroup level matrix, or excuse me, a subgroup. Each path will have an individual level weight to it. So we have different weights for each individual, but this denotes that these are paths that are found in subgroups. And then this is for the lagged effects. Same pattern of these are the subgroup effects with the individual level estimates. And then we finally have our individual level effects, which the structure of these matrices will vary across. And so that's kind of formally the whole model. And so I just randomly showed subgroup B here, but we could have easily shown any subgroup. All right. So we simulated this, going back to our simulated data that we showed before. Again, we had three different factors: number of individuals, number of subgroups, and degree of heterogeneity. So when we did the subgroup GIMI results, we recovered 93%, which is an improvement from before where we had 92. And then here we had better recovery of direction by doing a subgroup. So our initial kind of probe into this is that we do actually get better recovery when we have subgrouping level paths added, and when we do the subgrouping in the model selection procedure. And our recovery of subgroups was just excellent at 0.91, with one being absolutely perfect. Yeah.
Can you say something about the strength of the paths that you simulated?
Sure. So what's noted here, just to be clear, is the number of people who have the path. So the path width indicates that the whole group had it. So these black ones are group level, and they're also thicker. Maybe hard to tell here. And then these paths were, excuse me, they were. So in this case, only 25% has that path, for instance. And then as far as the weight goes, for the autoregressive, those are higher than the paths that are cross-lag, or the cross-lag paths. They are about 0.6, and then the cross-lags are 0.5. We also varied the weight across, I didn't want to put in too much information at once, but so we also varied the weight across subgroups, so that some had plus 0.2 to plus minus, or minus 0.2 around a 0.5 mean, so that we also differentiated across subgroups based on their group level path weight. Yes?
Were the data generated on linear Gaussian time series models or from TCM models?
Linear Gaussian time series. We used our approach for generating the time series data and correlated it, generated it exactly as the Smith models, just for fun to see how close they were. And then we correlated it with the Smith models, and it's very high, like about 0.9. And so another reason why we bypassed the balloon model is because this is hopefully going to be used beyond functional MRI. We're also using it in daily diary studies and other sorts of studies, so we just wanted to get kind of general time series data. So this is, yeah, and I didn't mean to be unclear about that. So even though we do have 10 ROIs here, this isn't generated in the same way that Smith generated their data. All right, so this is the RAND index, which indicates from 0 being the worst and 1 being the best, or the perfect recovery of the subgroups. So here we have subgroup number 2, 3, and 4 subgroups, and pink or red is our correlation-based approach, where we would have everybody's correlation matrix, vectorize them, and then get a correlation matrix of their similarity. Blue being the MI-based, which means that after getting the group level paths, we take everybody's MIs, we vectorize them, we correlate them for a new correlation matrix. So the model-based, the one that we do after getting the group or the group level paths, outperforms once we get up to 4 subgroups. Both do very well for 2 and 3 subgroups. And then as we decrease our sample size, we see huge gains by using the model-driven approach, which is during model selection when we cluster based on the modification indices, as opposed to using the correlation matrices, which have the full information across all of the ROIs. We then looked, and this is for the equal subgroup sizes. So this has 25% of each subgroup in each case, and 33% and 50%. So then when we had disproportionately one group, it really throws off the correlation matrices, whereas the modification indices-based approach is working really well. So we were really concerned with how to best cluster these individuals based on their brain temporal patterns. And yeah, so following these results, we're moving forward with the MI-based approach because it seems to be superior over the correlation-based approach. And the correlation-based approach has been used by 2 other groups in the past year, and so that's why we were curious about testing it against that. Okay, so finally, and I think I'm doing good on time, we tested it on a empirical data set. I'm not sure if everyone's familiar with this, but so Abide is a public repository of brain imaging data from multiple sites, and we selected the NYU data since they had the largest number of individuals, and then we further selected those who had autism spectrum disorder diagnoses. The average age was 14.6. 87% female, or excuse me, male, which is typical for ASD diagnoses. And so this is publicly available data that John Ritchie at Virginia Tech processed for the purpose of the present analyses. This is our data pipeline. We first parcelate the brain regions of the brain into default mode network regions. We extract a time series for each region, for each individual. Abide has multiple pipelines where they have already pre-processed the data, and we are using the CPAP one. Then we run subgrouping GIME using these extracted time series, and then we obtain our results. And we see how that relates to other behavioral indices. This is our result of the group level, and I show this just to show you how much heterogeneity we see in some samples. This is actually more than I've ever seen. I've worked with quite a few types of data. All of the paths were individual level. The only group level paths were these autoregressive paths. And then you see a lot of people having this path, but it still didn't surface at the group level map. And so this is also my motivation, because when I was working with brain researchers, 5 years ago when I first started, 6 years ago, And we would get maps like this. They're like, well, now what do I do? And we didn't really know what to do because there's just so much. This doesn't really do much for data reduction. It's like now we have, 73 different models for 73 different individuals. Like, where do we even go from there? And graph theory does help, of course. Okay, so then when we broke it out into subgroups, we see things a little bit clearer. Although not on this projector because all of the individual level paths are coming up because they're too small. They were quite thin once we got to the subgroup level. But so you can imagine that there's a lot of gray paths going on here because there are. I can see them on here. But so what I want to draw your attention to is that this path opened up at each subgroup level. And so this subgroup was differentiated by not having that path. This subgroup also didn't have, well, I'll get to that. And then I highlighted here paths that were more likely to occur in this subgroup versus every other subgroup. And so we begin to see like that we can make a little bit more sense of these results. And then I mentioned that we could then relate this to behavioral scales, but that was a little bit ambitious because we actually only have one scale from this data set that we could use, and it's the Finland Adaptive Social Behavior Scales. They have other scales related to, in the VIBE data set from NYU, related to diagnoses, but this was the only one that was available that was based on their behaviors, which is what we wanted to look at. So, so it's often used, and it has these 3 domains, and within each domain it has 3 items that we used, or 3 subscales that we used. Receptive, expressive, and written communication, personal, domestic, and community daily living skills, and then for socialization, interpersonal relations, play, and leisure, and then coping. And so when we looked at, we just did a multinomial regression where we had C as the reference group since that was the largest. So what we can tell with the multinomial regression is how each of these, what predicts being placed in each of these subgroups. And what we found was that with decreases in your daily personal skills, you are more likely to be in subgroup A. With increases in your socialization, you're more likely to be subgroup A as compared to subgroup C. For subgroup D, they're differentiated much like subgroup A by having higher socialization as compared to subgroup C. This group wasn't differentiated at all, but they had fewer paths per person than seen in other groups. So they were predominantly, they didn't have a lot of connectivity between these regions that are default mode network where you reflect a lot of connectivity during resting state data. And so, but they did have, so they had the lowest degree and not related to any of the Finland behavioral measures related to being placed in the subgroup B. And so, yes?
The Finland results paired with the scans in the Abide network?
Yes. Yeah, so that's what, because it's a public repository and secondary data analysis, we don't have total control over the measures, but this was the most complete set that was there. That's why we chose that.
You can actually see your lines on that one.
Oh, cool. I guess I picked the wrong screen. Just because it was the largest, and so for the multinomial regression, we had something that everything was compared to try to identify what would statistically predict being placed into one group versus C. We could have chosen, other ones, but that just seemed to make the most sense because subgroup C, because it was the largest, we just figured maybe that was the most typical ASD profile or something like that. But then, we see that they have. You're more likely to be that in that if you have lower socialization and play, so maybe these do, they have higher play, but then this one does not have personal skills. So it's for daily living. All right, so just in closing, this is what we're finding for using GIMI is that it works with as few as 10 individuals. Once you get below 10, it seems to not have benefit of recovering individual level paths more reliably than just doing it at the individual level. And make sure your variables are not highly correlated, especially in brain processing. Sometimes you'll have variables that are overlapping, and nobody means to do this, but sometimes their screws are too big. So then we get variables that are correlated at 0.98, and of course that's not going to work for any sort of like regression-based modeling, such as structural equation modeling. And then arriving at subgroups, it seems to work very well for at least 25 individuals. Data-driven searches, I always get in trouble just to kind of preempt anybody's question of, well, what about hypotheses? I'm not saying that we shouldn't have hypotheses as a science, but more just that sometimes it's helpful to have these data-driven searches. And I know for some people here I'm speaking to, fire, but yeah, I'm going to say that these are a replacement, but they could certainly help in forming hypotheses or guiding our searches for finding replicability. So GIME provides data-driven models of temporal relations. We can get now subgroup and individual level paths. And during model selection, individuals are placed into subgroups, and this can reveal new things, hopefully. We just, as I mentioned, it's now a CRAN. It's not now on CRAN, so there's no need for MATLAB and LISTRO. And then, but these two features, we have GUI now and subgrouping, but they're not in the CRAN package yet. And to my collaborators who work in this to be possible. These three up here are the ones that help a lot on this present project. That's it.
So these were in the simulated arresting state
Yes.
cases, the empirical case of arresting state. But if you do autistic spectrum subjects, or if you do ADHD, or lots of neuroatypical groups, and you give task-related scans, aren't your subgroupings going to begin to fracture enormously? That is to say, if I give autistics, say, a face-following task, and I give them an attention task or a direction task or etc., I may get different splittings, different subgroups for each task I might get them for the normals as well, but pretty soon I'm going to have a humongous set of subgroups. Yeah, and so one might worry that you might as well just think each individual is a distinct guy.
What if you didn't find different subgroups across all of these tasks?
Well, then that would be interesting, wouldn't it?
Because maybe I guess part of the motivation that I hear for using resting state data is that it's not going to be contingent on whether or not the person's paying attention to the task or if their ability is their ability doesn't matter, and that what others have shown is that resting state data does map onto functional data when they're doing a task. These networks that we see in resting state, we do see on task. And so presumably, maybe it is possible, but we haven't looked yet, that maybe we would see some consistency in the subgroups. And then if they are different, that will be very interesting. But but then that's a problem for any type of analysis.
No, I wasn't suggesting it was a problem for your analysis, just for what we can do with it in trying to find useful, clinically relevant subcategorizations, say, for autistics. Yeah. And if it turns out every time we give a different task, we get a different fragmentation, it would not be happy.
Well, I'm hoping this will help with, particularly for ADHD, identifying.
I'm sorry?
I was hoping this would help eventually with ADHD and identifying the best medication, or, because it seems like there's a trial by error method, and so, yeah. Do you have a question?
Yeah, you've played in your simulations with what happens with different numbers of ROIs and with different lengths of time series.
Not yet, but we will. Yeah, so we've been using 10, and in previous simulations that weren't focused on subgrouping, we've used 5 and then up to 25 for simulations, and it seems
for number of ROIs.
And so it seems to work well up to 25. After that, it's just computationally R kind of breaks down, and so so we just stop at 25. But for lengths of time, I haven't. I said I didn't do it, so I just haven't published it. So there's we know that you can go as low as 75, t equals 75, and it still works. Once you get down to 50, you start to have lower recovery. Okay. For like a 10 ROI situation.
Okay, so that's like the number of TRs.
Right. Yeah. Did you have a question, Aiden?
Well, I was just thinking about the notion of which task, and it could be that there might be the appropriate, clinically there's these appropriate tasks. So when it comes to traditional neuropsych testing for ADHD, you put them in front of a really boring task or something like this. But you could imagine it either being a battery of tasks or and picking, testing out which one might be the best for the given diagnostic group that you're interested in. And so it may not just be that resting state's the best. There may be a particular task, in which case particular patterns of connectivity might be the right one.
Yeah, that's a good point. Because also it's going to be based on your ROI selection. If you select ROIs that don't differentiate within ASD, then your subgroups will be meaningless because it doesn't matter.
Like any measurement model.
Yeah, right.
And then I had a crazy idea. Well, I think you might not like it, but what if you had a battery of tasks and you subgroup based on the nested structure within cross tasks? So for each task, you had a different set.
Right,
You know what I'm saying?
Yeah.
So a higher order cluster.
So cluster, like.
Cluster on one's performance across different tasks.
Yeah.
For a different specific task.
It
Seems
would
like
work.
a lot.
I like it. Yeah. I do like it. You're wrong.
And then just related to that, maybe if you had information on medication response.
Yeah.
You could see which tasks will predict, who does better and which.
Right. Because that's ultimately what I want to get my hands on is like individuals with and without medication and see like how things kind of go. Yeah, according to that. Mm-hmm.
So you're assuming that it's a time series stationary.
Yeah. Huge assumption. I know.
Yeah, I'm just wondering, particularly if you go to tasks.
Yeah.
I mean, for resting state, that's one thing, but if you go to tasks, whether that might be a problem.
So there's two things for that. Like if the events are spaced out well enough, we have integrated within it hemodynamic response functions so that we can model the task. We don't really keep it up because we're still trying to figure out the best way to do that. But if it's a block design where they're repeatedly shown, like if they're following a face for the whole block, then presumably it might be stationary, but then you do have inhibition and learning effects. So it's definitely probably not stationary.
That actually brings up a question.
Uh-huh.
So on the Smith simulations, yes, the original gimme before all of the subclustering, using 50 subjects did as well as almost anything. But there was one class of problems for which it uniquely did pretty well, and that was non-stationary case. And I wonder if you know why yet.
No, because the assumptions in our models are that it's stationary. I think that there was just enough signal for us to pick it up because the connections existed as they simulated the data. They did exist, and they just varied across time. I think it must have been strong enough for enough time point, right?
I don't know. It screwed up everything else. I mean,
yeah.
we tried prayer, and it still screwed up.
You really tried everything. Yeah, I don't really know. I just assumed the parameters that they simulated were favorable to us, kind of like the Butterworth filters seemed to work well in our case, and then different filters are.
So you haven't. So I guess there's a couple of other things I would wonder about whether you've tried simulation with other non-stationary time series to see how you do, and whether you've looked at distributions that aren't Gaussian.
We have not looked at distributions that are not Gaussian. We have looked at non-stationary data in GIME, and so what we did was we simulated non-stationary data, and then we ran it through GIME. We did get the correct effects, most of them, but then in the secondary analysis, we used a common filter to come up with time-varying effects so that we could see how each, for instance, a path between two regions are varying across time. And that worked well in that two-step approach. But again, we simulated the data in that case. Yeah, so I guess we should try our time varying approach on the Smith data. But I just assume there's enough signal to noise for us to pick it out with this that maybe other approaches aren't as sensitive to. And maybe taking into account the lagged effect. No, because that would vary too.
Yeah.
Yeah.
It's a miracle.
I prayed a lot. Shouldn't joke like that. I'm sorry. Joe.
Your R version of the 3D
Mm-hmm.
model. How many variables can it go into?
We've tested up to 25, and it takes a really long time. It takes much longer. So we used to use Lisrow, which is a structural equation modeling program. It's proprietary. And we used Lisrow and MATLAB, and that was just a little bit clunky to talk back and forth. And every time Lisrow changed anything, I had to change everything in MATLAB code. So that wasn't sustainable. And so we moved over to R, and it's a little bit slower, but then it has the added benefit that nobody has to buy anything. And some other improvements. We use Levon, I should say that. So Levon is an R package within R, made by Yves Rossel at Ghent University, and it's amazing. And he seemed to work out some kinks in M+ and Lisrow, and so it's a little bit more precise, I would say. Yes?
So I understand what it means clinically when you find structures which are
Mm-hmm.
what does it mean? What is the clinical significance when you find structures that you control? The subgroup partially known and partially controlled. What is the interpretation of that?
Right. For me, I look at it, and I'm not a clinician, so I have to sit with that. I look at it as there are some sub-threshold controls, or controls might have some similar biological underpinnings that somehow they don't manifest the behaviors. And I feel like those are the controls we need to be looking at. So in the ADHD example, where we have the majority of the ADHD in subgroup B, why are some controls biologically placed in that group? From their biological brain activity. And then what are they doing? What skills do they have that are preventing them from being diagnosed with ADHD? It, I think, would be like an interesting train or a line of research to look at those controls and say, why aren't they meeting the threshold for ADHD? What are they doing that's different than those meeting the threshold? Maybe we can learn from them.
When you see something that he was asking, do you handle the fact that most of the ADHD patients were receiving medication? I mean, I read that you made like a washout, but if you use medication during this important phase in brain development, how do you know all these changes and all these subgroups are not changed by medication instead of ADHD?
You're absolutely right. And I don't know the go-around. I mean, the go-around would be to find children who were recommended to be on medication but not given it for whatever reason. As parasympathetic, you're absolutely right. We could be, even though you mentioned the washout, like the 24-hour period where they're not on medication before the scan. Yes. But you're right, that doesn't get around all of the brain changes that are occurring by taking the medication every day. It's even out of their system for that day. Yeah, that's a good point. Yes.
Well, I got more questions.
All right.
So,
I have time. I don't know if else.
Sure. We're not going any place. So, you've done this all with fMRI, but it's easier and cheaper to get data from ADHD people and normals using EEG. You put a cap on them. Years ago, I did graphical model studies with EEG data for ADHD and normal subjects and ADHDs on and off medication. And I got different graphs for the different groups. It was pretty primitive in those days. Do you think the same techniques would work? You might not have the same causal interpretation, but you would certainly get graphs and clustering, whether they would correspond to causal relations is less important than whether they would lead to useful classifications.
Right, and it's a cheaper approach too.
Yeah, it's much cheaper.
I think it would be worth trying. I don't use AUG data, so I would need to pair up with somebody who's familiar with it. Yeah, but I think that would be
There's no reason why you couldn't.
right. True. I think, yeah, a lot of colleagues with it. Yeah.
I think we should let you go.